Good Sunday afternoon, calculus friends. We are here today to finish up chapter 4.3. This is going to be part 2. There may be a part 3. We'll see how long this video goes. Just as a reminder, the last lecture, 4.3 part 1, we talked about the first derivative test. So let's put that out here. So we're talking about how derivatives affect the shape of curves. We used our first derivative to find the precise location of local maxes and mins. In order to find our local maxes and mins, we found all the critical values for the function f of x. That is, we look to see where the derivative is 0 or where the derivative is undefined. Don't forget these guys. That's the ones people tend to forget. Once we have all our critical values, we put them out on a number line and we see how the derivative behaves before, between, and after the critical points. The derivative changes from positive to negative, so we go left to right at the critical point. Then we have a local maximum. If the derivative changes from negative to positive, then we'd have a local minimum. So this would be positive to negative would be this, so it would have a local max. If the derivative changes from negative to positive, the function changes from decreasing to increasing, would have a local min. And if the derivative does not change sign, it's either both positive or both negative, then there is neither a local max or min at that point. So let's do a review problem, one a little bit more difficult to get us going on our local maxes and mins. So let's find all local extreme points for the function, the cube root of x squared minus x, and determine the intervals of increase and decrease. So the first thing we do is find the critical numbers. Now remember, the critical numbers are where the derivative is equal to 0 or where the derivative is undefined. My suggestion is to always turn all radicals into powers. So then we can take the derivative, bring the power out front, leave what's inside alone, drop the power by 1. 1/3 minus 1 is negative 2/3 times the derivative of what's inside. And now we are going to see how this, we're going to clean it up a little bit. 2x minus 1 all over 3 cube root of x squared minus x. Oh, all squared. All right, so now the critical numbers, to determine the critical numbers, we look to see where does the numerator equal 0 and where does the denominator equal 0. So all values of x will give us the critical numbers. Oh, it just started pouring. The critical numbers for this particular function. So clearly the numerator is easy. 2x minus 1 equals 0. We're going to have a critical number at 1/2. Now don't let things like cube roots, with all this other stuff going on, freak you out at all. So this derivative is undefined when the denominator is 0. Now notice this 3 is irrelevant. We can divide the 3 out. The cube root, the only time a cube root is equal to 0 is if what's underneath is equal to 0. So in other words, when x squared minus x equals 0. And we're going to, here, we can just factor out the x. And we get x equals 0 and 1. So we have 3 critical numbers for this particular function. We have 1/2, 0, and 1. 1/2 makes the derivative 0. 0 and 1 makes the derivative undefined. So now my second step is to take these critical numbers and put them on a number line and see how the derivative behaves before, between, and after these critical numbers. So I'm going to draw my number line. 0. Whoops, I really didn't need to put it that far over. 1/2. Let me do this better. Try that again. Just space them out more so I have more room to work. So 0, 1/2, and 1. So I'm just going to put 0 over here. 1/2 here, and 1. I'm going to see how the derivative behaves. It's 0 at 0. Oh no, it's undefined. Wow, I'm really messing this up. It's undefined here. It's 0 here. It's undefined here. So we want to see how the derivative behaves before, between, and after. The derivative behaves before, between, and after these critical numbers. So I'm going to pick any number to the left of 0. So let's just say -1, and I'm going to plug it back into the derivative. So let's bring that up here. So the derivative at, let's just say -1. Well, if I put -1 into this derivative function, I'm going to get -3 on top. The denominator, notice, is always going to be positive because if I put any number in here, I'm going to square it. And when I square anything, the result is positive. So that I take the cube root of a positive number. The result is always positive. So you can do the algebra out. You can actually plug it in and do the work. Or you can just use sort of common sense here. Denominator is always positive. If I put -1 into the numerator, I get that my derivative is negative to the left of 0. If I pick any number between 0 and 1/2, let's see, I'm going to pick maybe a quarter. And if I put a 4th in, remember the denominator is always positive because we're going to square it before we take the cube root. So really what I'm focusing on is the numerator. If I put a quarter into the numerator, I get 2 times a quarter minus 1, which is a half minus 1, which is negative. So at this critical number, the derivative did not change signs. It's negative and then it's still negative. Let's see what happens between 1/2 and 1. I'm going to put in 3/4. So I put 3/4 in back into my derivative. If I put 3/4 in here, I get 3/2 minus 1, which is positive over something positive. So the derivative is positive here. So my derivative went from negative to positive. So -1/2 happens to be a local max or a local min. And then I'm going to pick anything to the right of 1. Anything, 2, 200, it doesn't matter. We're going to stick it into the derivative. If I stick 2 into the derivative, my numerator is 3, my denominator is positive, so it's positive. So we have 3 critical numbers, 0, 1/2, and 1, but the derivative only changes sign at 1/2. So if my derivative is negative, my original function is decreasing. So the function decreases, goes through this point, and it continues to decrease. Goes through 1/2 and then starts to increase, and then the original function passes through the point x equals 1 and continues to increase. So it's going to decrease, decrease, increase, increase. So the only critical number that produces a local extreme point would be x equals 1/2. So we have a local min at x equals 1/2, and the minimum value, read the directions carefully. Does it ask you where is the minimum located or what is the value? If it asks for the value, it wants you to stick it into the function. And if you stick 1/2 into the original function, so we're going to go way back up here to the original function and stick 1/2 in to the original function to find the coordinates of that local minimum. And if we stick it in here, we're going to get the exact value, which is the cube root of -1/4. And seeing that's a nice number, we're just going to leave it at that. And then we're going to make our conclusion here. We're going to say, therefore, we have a local min at x equals 1/2. The minimum value is equal to the cube root of -1/4. The function will decrease forever to the left of 1/2. It's going to decrease forever. It's going to hit 0, and then it's going to increase forever. So it's decreasing on -∞ to 1/2. We go left to right on the number line, and then it's increasing to the right of 1/2 to infinity. So I'm going to take a minute and just graph this guy really quick and see if we can see this. All right, graph, let's do clear. All right, and I'm going to graph the cube root function x squared minus x to the power cube root. You can use your cube root value, or to keep in mind that cube roots are equivalent to fractional powers to the 1/3 power. All right, I'm going to graph this guy. Am I in a good viewing rectangle? There we go. Comes down and then shoots up. So let's zoom in right here. We can see that it reaches its low point right at that point right there. So I'm going to kind of go over here a little bit. I'm going to zoom in, see what this looks like. Boom, decreases, decreases, oh, hits 1/2 and starts increasing. So the coordinates at that point right there are x equals 1/2, y equals the cube root of -1/4. All right, so moving on to the last topic in this section, concavity. So concavity is another way to describe how a graph behaves. Functions can be concave up, concave down, or they could be neither. A function is concave up when it's arched up, like if you think of a lens or something. So concave up means it's arched up, something like this. More precisely, using calculus, we say a function is concave up when all the tangent lines, if we pick any point and draw a tangent line on a graph that's concave up, the tangent lines always fall below the curve. Another way to look at concavity, or specifically concave up using calculus, is we move left to right on the curve. The slopes are increasing on the number line. So this may be like -2, this might be +0.5, this might be +1. So all tangent lines fall below the curve for concave up functions, and the slopes are increasing as we move left to right. Now be careful here because not all concave up functions make a complete bowl shape. We may have concave up and increasing. If a graph is concave up and increasing, think of an exponential function like y equals e to the x. It never has this part of the concavity. It can just be concave up and increasing, or it can be concave down. Oops, sorry, up. We're still in up and decreasing. So if you're concave up and decreasing, you're decreasing as you go left to right, but you're still arched up. So this would be like y equals e to the x. And this would also be an exponential function, but the base would have to be smaller than 1, so maybe 1/2 to the x, something like that. So this is concave up is shaped up like a bowl, left to right, it's increasing and arched up. If it's decreasing, it's left to right, we're going down, and it's arched up. So concave down, on the other hand, it's just the opposite. All tangent lines fall above the curve. Slopes are decreasing as we move left to right. So concave down is when it's arched down. So I think of an upside down soup bowl. And all tangent lines, no matter where we draw a tangent line, they fall above the curve. You may not always see the entire bowl shape. You might only see part of the bowl shape, but as long as it's arched down, it's concave down. So concave down and increasing. Concave down and increasing means we increase as we move from left to right, but we keep that arched down shape. So an example would be something like the square root function. Concave down and decreasing would be, well, if it's decreasing in an arched down, decreasing, go left to right, you're going to decrease, but you're going to do it in an arched down fashion. I'd say maybe, I guess, kind of cheesy, but if we just take that guy and flip him over. Nope, actually I'm not. It's not going to be it. What would be a one like this? I don't know. I have to think about that. Example of concave down and decreasing. Oh boy, I can't think of one off the top of my head. I should have thought about that ahead of time, but I didn't. But I'm sure you can come up with something if I gave you enough time. All right, one of my favorite tables is this guy. So I really, really like this. This is going to be super helpful if you can remember these relationships. All right, if the original function is increasing, wherever a function is increasing, keep in mind its derivatives are positive. And this relationship goes both ways. If a function is increasing on an interval, its derivatives are positive there. If a derivative is positive on an interval, then the original function is increasing. Wherever a function is decreasing, its derivatives are going to be negative. So when f of x is decreasing on an interval, its derivatives will always be negative on that interval, and the relationship goes both ways. If the derivatives are negative, then the original function is decreasing on that interval. So the derivative, we know itself is a function. So if our derivatives are increasing, right, we saw back here, if a derivative is increasing, then our original function is concave up. So anytime a function is concave up, our derivatives are going to be increasing. If our derivatives are increasing, then the function is concave up. Wherever the derivatives were decreasing, we said that the graph was concave down. So concave down. If a function's concave down, its derivatives are decreasing. Wherever the derivatives are decreasing, the function is concave down. But again, like I just said, remember, the derivative itself is a function. So the derivative of the derivative, if the derivative is increasing, its derivative must be positive. So if a function is concave up, its derivatives are increasing, and the derivative of the derivative is positive. So in other words, if the second derivatives are positive, the derivatives are increasing, and the original function is concave up. Wherever a function is concave down, its derivatives are decreasing, and where the derivative of the derivative is decreasing, wherever the derivative is decreasing, the derivative of the derivative is negative. So if a function's concave down, its derivatives are decreasing, and the derivative of the derivatives are negative, or the second derivative is negative. Whenever the second derivative is negative, the derivatives are decreasing, and the original function is concave up. So now we focused on at the beginning of this section where a function changes from increasing to decreasing or decreasing to increasing, and that happens when the first derivative changes from positive to negative or negative to positive. This change right here, we found where this changes, we look for the critical numbers in here. What we're going to focus on in the next talk, let's see, how am I doing on time? Yep, I'm going to do it. I'll stop this and do it in a minute. We're going to focus on what happens here when a function changes from concave up to concave down. How does its second derivative, what's the relationship here? And these points are called inflection points. So an inflection point is an inflection point for a function f of x is where a graph changes concavity. So if we have something like the cubic function, this is concave up here, concave down here, somewhere, so if we're walking along this curve, we can see it's arched down. For up here, it's arched up. So somewhere in here, it's going to change from arched down to arched up. This is what we're looking for, this point right here, inflection. Or inflection point. So to be continued. Part 3. See part 3. All right, see you in a few minutes.